Welcome to this Maths Made Easy video on the Newton-Raphson method. And to start with, let's just understand how we use the Newton-Raphson method. Now, the Newton-Raphson method allows us to find roots of an equation in the form f of x equals 0. So f of x equals 0. Now, the Newton-Raphson method is an iterative formula, and the formula is given as follows. xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Okay. Now this method iteratively finds the x-intercept of the tangent to the graph of f of x at xn, and it uses this value as xn plus 1. So what does that mean? Well, let's use this diagram here to illustrate that point. If we start with x naught here, what we do is we extend this until we meet the curve here, y equals f of x. And this forms a tangent here. Okay, this is the tangent to the graph of f of x at x naught. We extend this tangent until it intersects the x-axis here, giving us this root here of x1. And we repeat this process again. We again extend this point until it meets the curve y equals f of x, giving us another tangent here. And again, we just extend this until it intersects the x-axis. And we keep repeating this until we've reached a convergence that we're happy with, usually to a sensible degree of accuracy there. Okay, so that gives us everything that we need to understand the Newton-Raphson method. We also need to be able to understand why and state why the Newton-Raphson method can fail. So the first point we could make here is if the starting point of x0 is too far away from the actual root, then the Newton-Raphson method may diverge from the root. Another point we can also make as to why the Newton-Raphson method can fail is, and we can use this diagram to help us here, is when our gradient of the tangent at xn is close or equal to 0. As we can see here, as this gradient is close to 0, it's not going to cut through the x-axis until quite far away from our actual graph here. Okay, in that case, this causes us issues such as the root diverging rather than converging. And let's investigate what actually happens here when the gradient is equal to 0. And in this case here, if the tangent at a point on f of x is horizontal, like we can see here, then in this case this causes us two issues. The first issue here is, because this is just a straight line, and it's not going to intersect here with the x-axis, then we won't be able to obtain our next solution. We won't be able to obtain xn plus 1 in that case. So that's our first issue there. And take a moment now just to think about what else might be an issue here. Use the Newton-Raphson formula here to actually understand why this could be an issue. Now if we recall here our Newton-Raphson formula, well, that's xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Now, if we just recall this diagram here, why is this an issue? Well, this gradient here is equal to 0. So what we actually have here is a stationary point. Now this is a stationary point. What that means here is that the gradient f prime of xn is equal to 0. So therefore, f prime of xn equals 0. Now again, just take a look at the formula here, and hopefully it's jumping out at why this is such an issue. Because in this case, if f prime of xn is equal to 0, we're going to be dividing here by 0. And clearly we can't divide by 0. That would cause a mathematical error there. Okay, so that's another reason why the Newton-Raphson method can fail. And that concludes this Maths Made Easy video on the Newton-Raphson method.